Have you ever stopped to wonder how we even begin to describe something in motion? I mean, think about a planet orbiting the sun, or even just a coin flipping through the air. It seems crazy complicated, right? Well, the secret is actually to start super small and build our way up. So let's dive in and see how we can map out our entire universe one dimension at a time.
Right, let's start with that ball. Picture it. You throw it, and it doesn't just go forward, it goes up, it arcs over, and then it comes back down. It's tracing this beautiful, smooth curve through the air. So the big question is, how on earth do you describe its exact position at any given moment?
And believe it or not, the answer is way simpler than you'd think. The trick is not to look at that complex arc all at once. Instead, we're going to break it down into its most basic parts. We'll start with the absolute simplest kind of movement you can imagine and build our way up from there to the reality we all live in. Okay, so our first stop is the simplest universe possible. Imagine you're living on a single straight line. That's it. You can't go up, down, left, or right. Your only choices are forward or backward. Welcome to life in one dimension. A really good way to think about this is like a train on a perfectly straight track. It can chug forward and it can reverse backward, but it absolutely cannot turn off that track. That's the whole universe of movement in 1D. So, if you want to know exactly where that train is, you only need 3 little bits of info. 1, where did it start? 2, which way is it going, forward or back? And 3, how far has it gone? With just those 3 things, you can pinpoint its exact location on the line. Simple, right? But what happens when we want to get off the track? Well, this is how we build a new dimension. We take that first line, let's call it the x-axis for all that back and forth motion, then we add a brand new line running at a perfect right angle to it. This will be our y-axis for up and down motion. And boom, just like that, you've created a whole new world. And suddenly, we are not stuck on a track anymore. We can roam freely across a completely flat surface. This is the world of a video game screen, a piece of paper, a map. Welcome to two-dimensional motion. Now, our freedom to move has just exploded. We can go not just forward and back, but also side to side. Think about a ship on the vast flat ocean. It has 2 directions to play with, north-south and east-west. And by combining those 2, it can get to any point on the entire surface of the sea. And this is exactly where coordinates become so important. We can now give any spot on this flat plane a unique address using just 2 numbers, an x-coordinate for left-right and a y-coordinate for up-down. So you want to find point A? Easy. Go 2 spots to the right and 3 spots up. You're there. Every single point has its own unique 2-number address. But, our world isn't flat. So what do? We build again. We take our 2D flatland with its x and y axes, and we add one more line, a z-axis, that sticks straight up out of it, perpendicular to both of the others. And this new axis, it gives us depth, it gives us height. And with that one final addition, we've done it. We've constructed the world that we all know and live in, a world with length, width, and height. We have arrived in 3-dimensional space. Now we can describe the motion of pretty much anything. I mean, think about a drone flying through a city. It can move forward and backward down a street. That's the x-axis. It can move left and right between buildings. That's the y-axis. And it can move up and down in the air. That's the z-axis. It has total freedom in this 3D grid. So here's the key takeaway so far. With these 3 coordinates, x, y, and z, we have this incredibly powerful system. We can give a unique address to any point, any object, anywhere in the vastness of space. So we're done, right? We've described all of reality. Or have we? Think about it like this. If I told you, hey, let's meet at the coffee shop on the corner of 5th and Main up on the 10th floor. I've given you 3 perfect coordinates. I've told you the x, the y, and the z. But I've left out the single most important piece of information, haven't I? Yeah, because it is not enough to know where something happens. You have to know when it happens. And this brings us to the final and kind of mind-bending piece of this whole puzzle, the 4th dimension. It turns out that to truly lock down any event in our universe, whether it's catching a train or a star-going supernova, you don't need 3 coordinates. You need 4. 3 for the where, and 1 absolutely crucial coordinate for the when. This is the huge leap from just describing a location to describing an event. Space gives you the address, but space plus time, that gives you the appointment. The 2 are completely tangled up together. You can't have one without the other. And this unified, four-dimensional map of reality is what physicists call space-time. It's not just three dimensions of space with time just sort of happening on the side. No, it's a single, four-dimensional fabric that contains all events, everywhere, for all of history.
So, our universe, as far as we can tell, really is a 4D reality. It has three dimensions of space that we can move around in, up, down, left, right, and one dimension of time, which for us seems to only move in one direction, forward.
And this brings us all the way back to that ball we threw at the very beginning. To fully, completely describe its journey, you don't just need its 3D position. You need to know its X, Y, and Z coordinates at every single instant in time. That complete path through space and through time, that's its real story.
So, we did it. We built our reality all the way from a simple line up to a four-dimensional space-time. But that leaves us with one last, really fascinating question. If we discovered that time was just another dimension we move through, what else might be out there that we can't see? What could a fifth dimension even be? It's something to think about, isn't it?